Good morning, Science Alliance, or good afternoon, or good evening. It depends when you're watching, doesn't it? You might be watching on catch-up. Hello, if you're watching on catch-up. It's an IGCSE lesson. It's a lesson. I'm really excited about this one. Not because it's going to be an exciting lesson, but we're looking at the relationship between frequency and speed and wavelength. Get a piece of, I feel like I start every lesson at the moment like this. Get a piece of A4 paper. You got it? And fold it in half so that the shortest edges are together. And then fold it in half again, and that's it. That's the activity for today. Fold a piece of paper in half twice, and then open it up, and you should have 4 rectangles. We're just going to draw a wave on this bit of paper, and then I'm going to make you do a little bit of brain exercise. Some of it is revision of what we've been doing before, and some of it is new, because I want to get round to this relationship between wavelength and frequency and speed, because there are so many past paper IGCSE questions I haven't been able to give you because they involve this relationship. And once we've got this relationship down, you can just tackle all of them. So have you done that? You got it done? So we need to draw. It was quite easy when I did it on my own. It's quite hard to explain. I'll show you in a sec when you've caught up with me. You need to start at the top left side of your paper and draw a wave, but the peak of each wave has got to be over the crease. So start at the top, go down and then up by the time you get to the crease. Go down and up by the time you get to the crease. Go down and up. It's not that hard, is it? I'll show you. Let's do it together. Here we go. So, pen, start in the top left corner. It doesn't matter how big the wave is. It doesn't matter about the amplitude. You've got to go down and then up by the time you get to the crease. It doesn't matter at all if the waves aren't straight or accurate. All we need is just for a crest to be over each crease. That I'll show you like this. Yeah, see, that's terrible. Doesn't matter, does it? It's not going to hinder our learning one jot. And then when you finish, make sure that you finish with another half a wave like that. So you've got to the very top right. Okay, splendid. And when you've done that, can you label the distance between the peaks? Doesn't matter, any 2 peaks. Let's say that that's 2 meters, please. There. Once you've done that, you are ready to commence exercising your brain with some questions that I've got you. Oops. I must admit, when I did this, I quite got into this. I stared at what we were about to do and sort of worked on it for quite a long time. So if you feel like, oh man, I didn't have time to think, you might want to come back to this later. I found that this very helpful for understanding a lot of different aspects of waves. What I'd like you to do when you've got that done, and don't worry, it's going to be on the sheet, so if you haven't quite finished, doesn't matter. I'd like you to put your pen on the table just above the top right corner. You can just watch the screen if you like and then do it in a sec. And what I want you to do is, this is the exercise basically, is just move the piece of paper so that your whole wave on your sheet of paper goes past that pen in 1 second. You don't actually have to move it in 1 second, but just imagine that wave is going past that pen in 1 second, okay? That from the very start of the wave to the very end of the wave, going past that pen takes 1 second. And I have some questions that I'd like you to answer just about that. So here you go. Here are the questions. Best of luck. I've even drawn it. Look, I've even animated it on the screen just in case you weren't clear. So you should have a piece of paper that looks a little bit like this, right? The top of the peak at every crease. Put your pen in the top right corner and then watch. You've got to move the paper so it travels past the pen in 1 second. That's what you're doing, okay? So I'd like you to tell me, first of all, how many wavelengths are on your piece of paper. If you've been to previous waves lessons, you should be able to do this by now. How many wavelengths on your piece of paper? What is the frequency of that wave that you have there? By the way, frequency is how many waves per second, just to remind you. What's the period? We did period last week. What is the period of this wave? The period is how long it takes one wave to pass a point. And what's the speed of the wave in meters per second? And if you finish that, if you're like, oh, so easy. Well, if we double the frequency, but we keep speed the same, what happens to the wavelength? If we double the frequency, but we keep speed the same, what happens to the wavelength? What changes in your model if the wave travels half as fast? What changes in your model if the wave travels half as fast? And can you write an equation linking wavelength, speed and frequency by thinking about the answers? So the finished bit is supposed to be hard because you finished, so you deserve challenges. had a glass of water here for the activity and just drunk it. I'm just going to go and get some more. You don't need a glass of water, by the way, just for like a thing that I'm just going to very quickly show you. How are you getting on? Shall I answer the first couple so you know you're on the right track? You should have that there are 1, 2, 3, 4 wavelengths on this piece of paper. Did you get that? So the easiest way really to measure wavelength is from peak to peak, isn't it? But obviously it could be from trough to trough, or it could be from anywhere in the middle to anywhere else in the middle. Yeah, there's 4 wavelengths on that piece of paper. The frequency of the wave is 4, but why is that wrong? Why is that wrong? What have I done there? The frequency of that wave is 4. What have I done wrong? I haven't put a unit on, have I? So it means nothing. It could be 4 microhertz or millihertz or megahertz. So the frequency of the wave is 4 hertz. Right, I'll give you another minute just in case you're attempting the finished questions. Okay, chums, let's go through the answers. So the period, that's how long it takes one wave to go past a certain point. So if there's 4 waves taking 1 second, it must take one wave a quarter of a second. Oh, yeah, so that's 0.25 seconds. And the speed of the wave, well, it's in meters per second. I guess you might have decided to do the speed of one wave, but which would have given you the wrong answer. The speed of the wave is like how much of it travels past in 1 second. So 8 meters goes past in 1 second, yeah, because we've got 4 wavelengths that are all 4 meters. So the speed of the wave is 8 meters per second. Okay, let's just do these little finished questions then. If we double the frequency but we keep the speed the same, what happens to the wavelength? Well, here, look, I've drawn it on. We've doubled the frequency. Now there's twice as many waves per second. What's happened to the wavelength? Well, it's halved, isn't it? You can see that it's halved. There's 1 wave there, and there's 2 waves in the same space below it, right? What changes in your model if the wave travels half as fast? Well, did you try this? What changes in your model if the wave travels half as fast? Let's do that. So I'll put my pen back. What does that look like? Well, I'll say that if it's travelling half as fast, then in 1 second, instead of the whole wave going by, only half the wave travels by, right? So 1 second's gone by, but only half of the piece of paper has travelled. So what has changed? Well, wavelength hasn't changed in our model. This is not a good model, actually, because wavelength usually does change. We will talk about this later. But in our model, wavelength hasn't changed because it can't, because we've just drawn it on in pen. So what's changed is obviously the speed of the wave, but also the frequency, right? So now how many waves per second? Only 2, okay? Right. So the frequency of the wave has halved as well. And then I asked you, what solid question, can you write an equation linking wavelength, speed and frequency by thinking about those answers? Maybe you did, maybe you didn't. Here's some multiple choice. I want you to keep thinking about units and how you don't have to remember equations, you can work them out using the units. So maybe I've made this look more complicated than it needs to be. Which of these must be correct, okay? If wavelength is measured in meters, frequency is, well, it's really measured in per seconds, isn't it? Hertz means per second. And speed is measured in meters per second. Which one of these works out with the units? Is it wavelength equals frequency times speed? Speed equals frequency times wavelength? or frequency equals speed times wavelength. Which one of those must it be? The other two of them just don't make sense if you look at the units. I was getting some mixed responses to this on Facebook. Some people were saying the third one, but that would be waves per second equal meters per second times meters. So it can't be that, because if you take meters per second and you times them by meters, you're timesing meters by meters. So if you times speed and wavelength together, the unit that you got would end up being meters squared per second, which is not right, is it? That's not what the unit of frequency is. And the top one, you're timesing waves per second by meters per second. So you'd have per second squared. So the unit from this equation is meters per second squared. So it must be the middle one, right? If we times per second by meters, you end up with meters per second. Yay! Well done if you got that, and if you didn't, it doesn't matter at all. We'll just keep going through it to help you understand. This is the equation. Speed equals frequency times wavelength. You will see it written in these symbols. V, you remember, like velocity is speed. F, the only one that makes sense, really, represented frequency. And wavelength is this beautiful little Greek symbol called lambda, which I was having fun trying to write backwards yesterday for the Facebook lessons. So, this is our equation. And we've been talking about all the different bits of this equation for quite a long time, haven't we? I'm not going to write the whole thing on the board. I'm going to do probably really annoying for some of you thing. I'm going to write speed equals frequency times lambda. Are you okay? So speed of the wave equals its frequency times, you remember that's wavelength, yeah? So just like all equations, if you change one thing, you change the other things. We've talked quite a lot about how if light hits a glass of water, then it slows down. The speed changes. But just like if this was an equation, hi wormy pen top of the Joe made me. If this was a normal equation, like, I don't know, 6 equals 3 times 2, if this number changes, like, I don't know, say we write that this is suddenly this has gone up to 9, you've got to change something else, haven't you? You can't just say, oh, the speed changes. Something on this side's got to change as well. And it does. So later on, we're going to talk about what changes when you change certain things. But I just want you to have a little practice at that equation first of all. So if you've got a calculator on you, hopefully keeping it fairly simple here, just to give your brain some exercise using wave speed equals frequency times wavelength. There we go. F equals V equals F times lambda, and I've even put it in a little triangle for you for those of you who like that. You could do it propping up a little bit, couldn't you? Luckily I brought Lego. Is that okay? That's too much. Right, I'll read you the questions and you can just get going. A water ripple has a wavelength of 2 meters and a frequency of 6 hertz. How fast is it travelling? So you've got a wavelength, you've got a frequency, and you need a speed. Okay, I'm hoping you'll be okay with this. Then you've got to start rearranging. The ripple slows down, it's a clue, to 9 meters per second. Its frequency doesn't change. What is its new wavelength? So you've got to know that wavelength is speed divided by frequency for that one. The speed of sound in air is 340 meters per second. What is the wavelength of a sound wave with a frequency of 200 hertz? Light travels at 300 million meters per second in a vacuum. What is the frequency of a radio wave with a wavelength of 2,000 meters? And then, can you give me an answer, please, in kilohertz, because we need to practice that kind of thing. And if you've got that finished, sound travels 340 meters in 1 second. How long does it take to travel 34 meters? Now, give your answer in milliseconds. Welcome, welcome, people who are just joining us live. No offence to the people who've been watching this whole time, but you haven't missed very much, really. Haven't really missed anything at all. You can pretend that the lesson just started with me telling you this equation, and then answer these questions, and you're good to go. Oh God, someone on Facebook yesterday was like, aha, there's the Theatre of Science fly. It's not the same fly. This fly is not a mascot for Theatre of Science. Just one new really annoying blue bottle. Right, I'll open that up. And then you can hear the bird singing and hopefully fly will go away. Maybe a bird will eat the fly. That will work out well. I'll give you 20 seconds and then we'll go through the answers. If I'm going too fast for you, then, well, don't forget it's on YouTube, so you can always pause it. Ah, we've got birdsong and jets flying past. It's all so physicsy and wavy out there today. Okay, let's go through some of these answers, shall we? Don't worry if you haven't finished this, because these questions were for people who had worked quickly. Right. A water ripple has a wavelength of 2 meters and a frequency of 6 hertz. So you just plug it into the equation, times them together, and you should have 12 meters per second as your answer. Please, please, please give yourself 1,000 ticks and smiley faces and say well done to yourself if you have written in your units. So important, especially as we start doing more complicated maths. It's such an easy way of checking. Look, if you know that hertz means per second, and obviously that's meters, then it makes sense. It's just like per second meters. Oh yeah, and the answer's in meters per second, so that works. I do that all the time, and especially if you're in an exam and you're nervous. So now we've got a new speed of 9 meters per second, but the frequency is still 6 hertz. So this time you do the speed divided by the frequency to get the wavelength. So it's 1.5 meters. The speed of sound in air is 340 meters per second. You will be expected to know that. What is the wavelength of a sound wave with a frequency of 200 hertz? Well, again, it's just speed divided by frequency. So you should have got 1.7 meters. Light travels at 300 million meters per second in a vacuum. What is the frequency of a radio wave with a wavelength of 2,000 meters? This was perplexing some people on Facebook yesterday. Don't forget that all electromagnetic waves are basically the same, right? So radio, microwaves, X-rays, light waves, we've talked about this. They all travel at the same speed. They're basically the same waves, just that the wavelength is different. So radio waves are just light waves that you can't see. That's why we often call light waves visible light waves. So you just used that speed. And you should have got, I've written it down differently just to get you used to this. Are you okay with 3 times 10 to the power 8 is just the same as 300 million. That 8 basically tells you how many zeros to put on the end. Divided by 2,000 meters, which is 150,000 hertz. Give your answer in kilohertz. Well, there's 1,000 hertz in 1 kilohertz. 1,000 hertz in a kilohertz. So if it's a kilohertz, it's going to be a smaller number, and you divide it by 1,000. So you basically knock off 3 zeros, and it's 150 kilohertz. Let's quickly go through the other two. Sound travels 350 meters in 1 second, so how long does it take to travel 34 meters? Well, you've divided that 340 by 10 to get 34, so you can just divide this 1 second by 10 as well. So it's 0.1 seconds. And to get that in millihertz, that was quite tricky, I think. If 1 second is 1,000 milliseconds, 1 second is 1,000 milliseconds. So if you want to put 0.1 seconds into milliseconds, it's definitely going to be a bigger number, right? Because there's loads of milliseconds in there. And this time you have to times it by 1,000. So what I always end up doing is just imagine moving the decimal place. So if you move the decimal place 1 back, that would be timesing by 10, and you'd have the answer of 1. If you move it 2 back, that would be timesing by 100, but you move it 3 back to times by 1,000. So the answer is 100 milliseconds. I think a new fly has joined us. Oh no, it's gone. Right, while you're thinking about that, I'm just going to quickly shut this off. Right. Okay, come back up here for me. Hello. Now, there is a bit of a problem with this equation. It's not a problem with the equation. The equation's fine. The equation's great. But the problem with this equation is you imagine that you can just plug numbers in. So you're like, oh, okay, yeah, like if speed stays the same, then when frequency goes up, wavelength must go down. If speed goes up, one of these must have gone up. But that doesn't explain the science behind it, because that's not true. In the real physical world, one of these doesn't change and just change like either one of them. So, for example, frequency is dictated by just how much something is vibrating, like how many times per second the thing is vibrating. So if I create a wave with my slinky, the frequency of the wave, how many times it passes a point, how many waves pass a point per second, it is only dictated by how quickly I'm moving my arm up and down, okay? If I speak, then my vocal cords are vibrating at a certain frequency. So the sound wave is traveling through the air. If I decide to dunk my head in a bath and talk into the bath, is that changing the amount of times that my vocal cords are vibrating per second? No, it's not. So I would be shouting into air or shouting into water. They're different mediums, so the speed of my sound wave would be changing. But my frequency would not be changing. You can't change frequency unless you're changing the source of the vibrations, all right? So we've talked a lot about how light slows down when it hits water or glass, and it does. But obviously, light is caused by vibrations like in space, you know, from the sun. So hitting a glass of water is not going to change the vibration. It's not going to change the frequency of the light, because that's being dictated by something far beyond our control, but it is slowing down. So if speed is going down and frequency is staying the same, I'm just drawing like a not bothered emoji for staying the same, what's going to happen to wavelength? If speed is going down, if it's slowing down, frequency stays the same, what's happening to the wavelength? You're struggling with this, we can put our simple little equation on the board. Goes down, doesn't it, right? So if we change this speed now, so it's 2, and frequency set, what a horrible sum. If we change this speed so that it's 0, it's gone right down, and frequency is going to stay the same, what happens to the wavelength? The wavelength has to go right down as well, yeah, to keep the sum balanced. And that is indeed what happens. When light travels through water, the wavelength gets shorter, which is why someone was picking me up on Facebook very wisely on my first little question we did when I said, if the wave slows down, what happens to the frequency? I was very careful to say in our model what happens. Like if we slow this wave down, the frequency changes. That isn't actually what happens. What would happen was the wavelength would change. It didn't work in our model because we'd drawn it on in pen. So, but anyway, well done if you spotted that. Right, I think you can have a little go at these questions then for me, see if you've understood that. What causes speed, wavelength and frequency to change? Let's think about that. Pretend you bob a toy duck up and down in a bath and ripples are produced. What could you do to the duck to change the frequency of the ripples, the wavelength of the ripples, and the speed of the ripples? And if you're okay with that, a high note and a low note travel through water. What do they have in common? Is it speed or frequency or wavelength, or is it a couple of those things? That's a good one, isn't it? Oh, pleased with that question. That's a good bit of revision for sound. I think it's quite tricky, this. I wouldn't probably do this if it was just GCSE physics. This is IGCSE. That's what I like about IGCSE, actually, is you get to go a little bit deeper. But when fly's back, how are you back? Are you a ghost fly? There's 2 of them. I'm just going to leave the door open. Right, you bob a toy duck up and down. What could you do to change the frequency? Well, hopefully you said you would change the frequency of the bobs, like the speed of the vibrations, how fast you were bobbing the duck up and down. And if you change the if you change the frequency, you would also be changing that too, okay? You can picture it. You can do it with a glass of water. Recreate Jurassic Park. If your finger is bobbing up and down in a glass, you will see beautiful ripples appear. And if you bob faster, actually should have got you to bring a glass of water. That's quite clear. Yeah, if you bob faster, then you get a higher frequency, more waves per second, which means that the wavelength has changed, right? What could you do to change the speed of the ripples? The answer is there is nothing you could do with your finger or your duck or whatever to change the speed of those ripples. So that you could change the properties of the water. You could change something to do with the water. We'll look at that in a sec. But there's nothing you could do with your finger to change the speed, because speed only changes when the properties of the medium change, if you like. A high note and a low note travel through water. What do they have in common? The speed, because they're both travelling through the same medium, so they've got speed in common. I even wrote it on the board for you. Look, that's a high note and that's a low note. So you can see the frequencies are different and the wavelengths are also different, but the speed would be the same because it's the same medium. Okay, so I've said that actually you can change the properties of like water or air to change the speed of a wave. This is a great fact. Let's have a look at this just before we go. Light travels faster through hot air, and this is what causes mirages like floating ships. So, I mean, if you know a little bit about particle physics, and we will talk about it later, this makes sense, right? Hot air, the particles have got more energy and they're further apart. So it makes sense that light would be less impeded, would be able to travel faster through hot air. Particles are further apart. Cold air, the particles are much closer together, so the light is going to be interacting with more particles. It's harder to get through. So I don't know if you saw this. You might be a bit young for this, some of you, but quite a few years ago it hit the news because a lot of people had looked out to sea and seen a ship that appeared to be floating. There is a photo of it on the internet. I'm so delighted that someone put this on Wikimedia Commons. There we go. Look at that. I'll zoom in a bit for you. It really does look like it's floating, doesn't it? Isn't that incredible? So it's just an optical illusion caused by the fact that light travels faster through hot air. So yeah, here's what's happening. It's good revision for refraction. We've done this a lot of times before, haven't we? If we say that the pen is a wave, a light wave, travels through hot air nice and fast. The bottom of the pen or a light wave hits the cold air, so slows down, but the top bit's still in the hot air, so it's still travelling fast, so it bends towards this person's eye. And then what happens? It sees this. Why? Well, because this person's amazing brain thinks, oh, well, I know that light travels in straight lines, and therefore the light that's come from the flag on top of the ship or whatever, it must have come from over there, but that's higher. So the image of the ship is formed above the sea. Isn't that brilliant? It's the same kind of situation with mirages in the desert. The air just above the sand is really hot. So the light travels from the top of this cactus quite slowly. It hits the hot air, the bottom of the wave speeds up, and you get this situation. So the human brain sees an upside down cactus on the ground. And, you know, your brain's quite smart. It sees an upside down cactus on the ground and it thinks, well, there must be some water there. That must be a reflection. It's very easy to see this if you're in a car on a very hot day. Have a look at the tarmac in front. And if the tarmac gets really hot, it's the same situation. The air just above gets really hot and it looks like there's water on the road or like oil on the road, but there's not. It's just your brain seeing a car reflected on the road and thinking, well, there must be something wet there. Right, have a go at these then, please. What is changing in these mirage examples? Speed, frequency or wavelength, or combination of the three. And also, back to this activity we did in our sound lesson. If we run a hand over the top of a wine glass and hear a note, and then we fill the glass with water, because we did, we hear a lower note, what has changed? Is it speed, frequency or wavelength? Or hopefully you're thinking, well, it must be a combination, because if you change one of the others have got to change. 10 seconds. All right, let's have a little think about it. So with the ship mirage situation, it can't be, it's my picture of a ship. I live in York. We think all ships look like that. It can't be the frequency that's changing, can it? It just can't be, because we're talking about light waves, and the frequency of light waves is dictated by, you know, space, the sun. So its speed, because it's slowing down, it's why refraction happens, and because it's slowing down, the wavelength is getting smaller as well. So I better write wavelength. Incidentally, this also happens with tsunamis as well. So another thing which we will look at in our ripple tank lesson in a couple of weeks' time. Another way that you can change the speed of a wave is in deep water or shallow water. So waves travel faster through deep water. So tsunamis, you can barely see them when they're in really deep water. Like literally ships could sail over them and not even notice. They're moving very, very fast. And when they get to land, obviously the amplitude of the wave gets a lot bigger as it hits the shallow water, but actually the wave slows down because it hits the shallow water. So the wave of a tsunami slows down, so the wavelength slows down as well. Right, this wine glass activity then, to finish, I love this one. We were running our hand across the top of wine glasses and getting a sound. Works better on the table, doesn't it? There we go. And then we were filling it with water. And we were getting a different note, a different pitch, a lower note. Oh. So what's changing there? Did you get that it's actually the frequency that is changing in that case? Because it's a different pitch, right? So it must be the frequency, because that's a low note has a lower frequency, and a high note has a high frequency. So we're changing the pitch, we're changing how quickly the glass particles are vibrating, but we obviously can't be changing the speed because the low note and the high note are both travelling through air. So if frequency changes, then wavelength does change. So in that case, it was frequency and wavelength. Well done if you got that. Whew, okay, that is the end of our frequency. I'm so happy I can finally set you pretty much all of the IGCSE questions there are about waves, because they all involve this in some way. So I'll put that in the PDF on my Facebook group if you want to go and track that down, or possibly later today actually. I'll try and get it up for today. Thank you so much for joining me. We've still got 3 lessons on waves left. We get to look at the Doppler effect. Yes. We get to look at the practicals, and I'm going to try and do a kind of recap-y sort of quiz question lesson at the end as well, I think, which would be useful, because it feels like we've been doing waves for a long time. If you would like to support me, you totally can. There's no funding involved here. I just couldn't cope with the admin. The only way that I make money from this job is people signing up to support me with £5 a month. So if you go to my About section on YouTube, it takes you to this website where, yeah, you send me £5 a month and I do an IGCSE lesson just like this every week in term time, and I do an all ages lesson as well, which I'm sure would be suitable for you. There's one at 11 on coral reefs, and I do a Lego Storytime show as well, which again you are most welcome to come to. I will send you Theatre of Science magazine. If you are supporting me and you're watching this, you are well due a Theatre of Science magazine. Husband is, I think, actually taking the children away this weekend so that I can just sit down and just get it finished, because I've got a very thick issue on weeds, which is coming your way. But if you sign up now, I'll send you the weeds one when it's ready, but you'll get this one, which is on mould. I send you a free biodegradable plastic bag so that you can do a grow your own mould activity, and a choose your own adventure story in there, and a comic about the true story of how penicillin was discovered. I'm just going to go over to my Facebook page and see if any incredibly patient people are waiting to say hello to me, because every time I'm live on YouTube, I put a little post on Facebook saying, "You're watching live, then please come see me. Say hello." Here we go. I'm really excited. I hope he does. I mean, I did want to join them, but the idea of just spending 2 solid days just drinking coffee and writing about weeds for you lot is pretty exciting, actually. Is that sad? No. I love writing you a magazine. It's like writing you a letter. Oh, here we go. Oh, worksheets, question mark. Yep, if you click the title of the lesson in the post, then links to the worksheets are in the post. Hello, Russell, and hello, Sky and Evie. I hope you found the worksheets. Yeah, in the title on the post you've commented on. If you click on it, then all the links are in there for you. But well, you've done the lesson now, hopefully, so I hope you enjoyed it. All right, you lot, thank you so much for coming, and I'll see you very soon. Bye.